In this module, we move from quantum is a threat to here's how we respond. You'll see the main post-quantum algorithm families, how hybrid schemes mix classical and quantum-safe crypto, and what that means for performance and HSM integration. Harvest now. Decrypt later describes a simple but dangerous idea. Attackers don't need a quantum computer today. They just need to capture encrypted data now and store it. If that data must stay confidential for 20 or 30 years, it likely overlaps with the arrival of fault-tolerant quantum computers. At that point, today's RSA and ECC could be broken, and all that stored traffic becomes readable. So the key question isn't when will quantum computers arrive, but how long does my data need to remain secure? Quantum attacks don't hit all algorithms equally. Shor's algorithm is the critical one. It efficiently solves the math problems that RSA and elliptic curve schemes rely on. Those public key systems become fundamentally broken once large quantum computers exist, no matter how big you make the keys. Grover's algorithm is different. It speeds up brute force attacks on symmetric crypto and hashes, like AES and SHA-2 or SHA-3, but only quadratically. In practice, that just means doubling key and hash sizes to get back to similar security levels. Post-quantum algorithms also aren't equal to each other. Each family brings specific trade-offs you'll need to understand when planning HSM integration. Lattice-based schemes like Kyber and Dilithium are today's workhorses. They support key exchange and signatures with moderate key and signature sizes and good performance. Code-based options such as Classic McEliece mainly cover key exchange, but their public keys are enormous, which complicates storage and networking. Hash-based and multivariate schemes focus on signatures. They range from very large signatures to more subtle caution flags around their security assumptions, even when performance looks attractive. When people talk about post-quantum cryptography today, they mostly mean lattice-based schemes like Kyber, Dilithium, and FALCON. Very roughly, these use high-dimensional grids plus carefully added noise to create math problems that even quantum computers can't efficiently reverse. Their big advantages are good performance, reasonable signature sizes, and strong momentum in the NIST standards process. The trade-offs are larger public keys and the need for very careful implementation to resist side-channel attacks in HSMs. Fully embracing post-quantum algorithms like Dilithium or McEliece dramatically increases quantum resistance. But it also stresses your infrastructure. Huge public keys bloat TLS handshakes and other protocols, increasing latency and bandwidth. Middleware that assumed keys were just a few kilobytes may hit hard limits, or start fragmenting messages in unsafe ways. HSMs also feel the pressure. Memory quotas and partitions sized for classical keys can't easily store thousands of very large PQC keys. The core takeaway? Pure PQC deployments usually force broader network, protocol, and HSM upgrades, not just a cryptographic library swap. Hybrid cryptography takes a different path. You run two engines at once, a classical algorithm you already trust, and a quantum-safe algorithm designed for the future. Both protect the same operation, such as key establishment, and you only treat the result as secure if each side succeeds. If attackers ever break the classical part, they still have to defeat the quantum-safe part as well. This gives you cryptographic defense in depth. It lets you stay compliant with today's standards, while quietly building resilience against tomorrow's large-scale quantum computers. A hybrid handshake is simply two key exchanges running in parallel. One uses a classical algorithm like X25519, the other uses a post-quantum chem, such as Kyber, and each produces its own shared secret. Both secrets then feed into a key derivation function, which mixes them into a single hybrid shared secret. As long as either component remains secure, the traffic keys are safe. This design also preserves backward compatibility. If a peer doesn't support post-quantum, you can still fall back to the classical side. Hybrid or dual-layer trust anchors extend the same idea to certificates. You combine two signatures inside one certificate, a classical algorithm like ECDSA and a post-quantum algorithm such as Dilithium. The relying party only accepts the certificate if both signatures validate, so security now depends on two independent hardness assumptions. Operationally, this isn't free. CAs must issue and manage larger certificates, and validation services like OCSP and CRLs must understand and verify both layers. Designing PKI for this means planning for bigger objects, more processing, and careful algorithm lifecycle management. Introducing post-quantum crypto into an HSM effectively changes the appliance in 3 dimensions. First, firmware agility. The module needs updatable, side-channel hardened implementations of PQC and hybrid algorithms without requiring constant hardware refreshes. Second, key storage. PQC keys can be huge, so internal secure memory and key metadata models must scale up. Third, policy and APIs. Interfaces like PKCS number 11 or KMIP need new mechanisms, attributes, and usage flags for composite and hybrid keys. All of this has to happen while staying within existing FIPS 140 and common criteria validation boundaries. Think of quantum-safe migration as a repeatable loop, not a one-time project. Start by inventorying. Identify every public key use, how long associated data must stay confidential, and where algorithms are hard-coded. Then pilot, stand up hybrid TLS or dual-stack PKI in low-risk environments and measure the impact on HSMs, networks, and applications. Next, govern. Turn those lessons into policies, deprecate weak algorithms, and align with NIST and IETF guidance. Finally, monitor. Track PQC standards, update parameters, and regularly revisit your inventory and pilots. You're now equipped to think in terms of cryptographic resilience, not just individual algorithms. Keep 3 forces in mind as you design. The quantum threat is real today through harvest now. Decrypt later attacks. Hybrid schemes let you blend proven classical crypto with quantum-safe options. And modern HSMs provide the anchor that makes this agility operational, auditable, and compliant at scale.